Hello everybody, welcome to lecture 12. So this is the second lecture of week 6. It's really a continuation on from the last one where we defined the concept of dimension for a vector space and saw that all bases of a vector space have the same number of elements, and that of course is called the dimension of the vector space. So this is just a repeat basically of the last slide from the last lecture where we defined that concept and noted that consequence of the exchange lemma, that every basis of a vector space has the same number of elements. So we're not going to revisit the mechanics of the proof of the exchange lemma. We're just going to recall this key consequence of it and look at a few more consequences. Okay, but an example, first of all, about bases and about how we might find a basis for a particular space. So we're going to have a look at the space of all skew symmetric matrices in M3R, 3 by 3 skew symmetric matrices with real entries. So a matrix is skew symmetric if its transpose is equal to its negative. So it's kind of a complementary concept to symmetric matrices. But what it means to be skew symmetric for a real matrix, we'll just make a quick note about it, is if you have it's like a 3 by 3 matrix, generally can have entries A, B, C, D, E, F, G, H, I, something like that, if the entries are all completely independent of each other. So to be skew symmetric, this matrix has to be equal to the negative of its transpose. So when we take the transpose of this matrix, the entries on the diagonal stay the same. So in order for this matrix to be, for the negative of this matrix to be equal to its transpose, we need the entry in the top left entry to be both equal to A and to minus A. So A is minus A, same for the other two entries on the main diagonal, B is minus B, and C is minus C. If we have a B here in the second entry of row 1 of A, if we have a B here in the second entry of row 1 of A, then the corresponding entry in the transpose is in this position, and it should be minus B. So basically B and D should be negative to each other. Similarly, F and G should be negative to F and H should be negative to each other, and also for C and G. So a 3 by 3 matrix is skew symmetric if the three entries on its main diagonal are all 0, and the other three entries are negative of each other in opposite positions, in opposite positions corresponding to the transpose. So in positions that are sort of reflections of each other in the main diagonal. So for example, if we have an A in this position and this matrix is equal to the negative of its transpose, we must have a minus A in this position, and so on. So the set of all skew symmetric matrices in M3 is the set of all matrices of this type, where A, B, and C may be any real numbers. So an example of a skew symmetric matrix, I guess an explicit one, would be something like, we could have 0 here, 2 here, 1 here, 4 here, maybe. If we do that, we want the matrix to be equal to its negative transpose. So the entries on the main diagonal all have to be 0, and the entries in the lower left have to be the negatives of the opposite entries in the upper right. Okay, so one can check easily, and I'll let you check that this set of skew symmetric matrices does form a subspace. So that's saying that when you add together two skew symmetric matrices, you get a skew symmetric matrix as the result. And that if you multiply a skew symmetric matrix by a real scalar, that the result of that is still skew symmetric. So we've already kind of noted that in order to write down a skew symmetric matrix, you basically have a free choice for what elements, what entries to put in the upper right area there, those three positions. But once you've decided what to put there, everything else is determined for you. The three entries on the diagonal have to be all 0s, and the entries in the lower left region have to be the negatives of the opposite entries in the upper right region. So, you know, from the fact that it takes 3 free choices for the entries in positions 1, 2, 1, 3, and 2, 3 to write down a skew symmetric matrix, we could surmise that the dimension of the space of skew symmetric matrices is equal to 3, which is indeed true. If you want to write down a basis, I suppose one way to do it, and there are many different bases for this space, so this is certainly not the only way to do it, but if you wanted to write down your typical element of V, noting that it has these 3 entries A, B, and C in this upper right area, which can be sort of freely chosen, then you might sort of separate it out and say, well, okay, so this matrix is A multiplied by something, plus B multiplied by something, plus C multiplied by something. So it's a linear combination of 3 particular skew symmetric matrices with coefficients A, B, and C. So we could say the A appears in the 1, 2, and 2, 1 positions. So we've got A multiplied by this matrix, which has 1 in the 2, 1 position and minus 1 in the sorry, it has 1 in the 1, 2 position and minus 1 in the 2, 1 position. This one, which has 1 in the 1, 3 position and minus 1 in the 3, 1 position, and the C multiplied by this one, which has the 1 and minus 1 in the 2, 3 and 3, 2 positions. Okay, so what we're really saying here is that every skew symmetric matrix is a linear combination of these 3 matrices. The rest of the text here is basically just to introduce some notation, which is quite often useful when you're trying to describe kind of matrix setups. And that's to note that there is a general kind of convention of writing capital E subscript ij for the matrix which has a 1 in the ij position, row I and column j, and zeros everywhere else. So E11, for example, would have a 1 on the top left and zeros everywhere else. So and you don't really sort of specify what the size of the matrix is in this notation. That's generally taken to be clear from the context. In this case, it's 3 by 3. So this matrix, which has a 1 in the 1, 2 position and minus 1 in the 2, 1 position, you could write it as E12 minus E21. E12 would have the 1 here, and E21 would have the 1 there. So the difference E12 minus E21 is exactly that matrix, which is appearing multiplied by A. Similarly, we've got B here multiplying E13 minus E31, and C multiplying the third matrix. So, okay, so we're saying that every skew symmetric real matrix is a linear combination of these 3. 1, 2, 3. Okay, and we can also, so we're seeing, yeah, the set of those 3 matrices is a spanning set of our space of skew symmetrics. And we can also observe that it's linearly independent. And if you're in any doubt about that, or if you're wondering kind of how would you go about doing that, to show that these 3 matrices are linearly independent, we need to show that the only way a linear combination of the 3 of them can be the 0 matrix is if all 3 have coefficient 0. So if we so what we have written on the left-hand side here, on the right-hand side of this line, is essentially a linear combination of those 3 matrices. So if that linear combination was equal to the 0 matrix, well, by looking at the entry, for example, in the 1, 2 position, that would be an A from the first contribution plus, oops, there's a typo here, sorry for that, this should be a 0, of course, plus a 0 from the second contribution, plus a 0 from the third contribution. So the entry in the 1, 2 position, for example, of this linear combination of 3 matrices is just A. So if that linear combination is equal to the 0 matrix, the coefficient A has to be 0 because it appears here in the 1, 2 and 2, 1 positions. Similarly, the entry in the 1, 3 position in this linear combination is 0 from the first term, B from the second term, and 0 from the third term, so it's just B. So if a linear combination like this of these 3 matrices is going to be the 0 matrix, the coefficient B has to be 0. There's no other way that we can arrange to get a 0 in the top right entry. And similarly, looking at the 2, 3 or 3, 2 entries, we find that C would also have to be 0. So we can conclude that that set of 3 matrices is linearly independent. So in this particular instance, it's kind of relatively straightforward to show that, for the reason being that in the case of all 3 matrices, each one of them has a 1 in a position where all the others have zeros. And that tells you that the coefficient of that particular one would have to be 0 in any expression for 0 as a linear combination of the 3 of them. But in any case, we've constructed a basis with 3 elements of this vector space, the space of skew symmetric 3 by 3s, and we can conclude that since this basis has 3 elements, every basis of the space must have 3 elements, and the dimension of the space must be 3. So there are certainly plenty of different bases that one could write down and that one could construct. This one, I guess, is kind of the one that presents itself kind of naturally, but there are other bases besides that one for the space of 3 by 3 skew symmetric matrices. So that's an example, I suppose, of a construction of a basis and the determination of the dimension by constructing a basis. Okay, so I just wanted to mention that we can get a bit more mileage out of the work that we have put in to develop and prove the standards exchange theorem, or the standards exchange lemma. And there are a couple of lemmas here that are really kind of pivotal and really useful in constructing many different arguments. So the standards exchange theorem itself is, in a sense, the most important kind of technical ingredient in the proof of all these statements, but by itself it's not the most important statement and not the one that tends to get used the most, but it's really it's a key technical step in the proof. But the the consequences of it are by themselves tend to be more important and more directly used. So here are just a few of them. So the standard exchange is just recalled there so that we can remind ourselves of what it says, that the number of elements in the linearly independent set cannot exceed the number in any spanning set. So one really important consequence of that we've seen already is that all bases for any given vector space have the same number of elements. But here are a couple more consequences of the standard exchange theorem. Okay, so the first one, every linearly independent subset of a vector space V which has dimension n with n elements is a basis. Okay, so our setup is we've got a vector space V of dimension n. So what that means is that we have a vector space V and some basis of it has n elements. And that means, as we know, that every basis of it must have n elements. So what we're saying in lemma 1 is that if this is the situation, then every linearly independent subset with n elements must be a spanning set. Okay, and the reason why that must be true is because, so just to give a kind of line of proof for lemma 1 here, if we have a linearly independent set with n elements and it's not a spanning set, then there's some element of the vector space that isn't in its linear span. So if L has n elements, so let's say that L is V1 up to Vn, is linearly independent, okay, what we want to show is that if L is linearly independent and has n elements, then it must be a spanning set, because that's what it means to say it must be a basis. But if it's not a spanning set, okay, if that's the situation, then there is some element V of the vector space which is not a linear combination of the elements of L. So it's not in the linear span of L. But if that's true, then we could add V into the set and we'd have a linearly independent set with more than n elements, which is not possible by the standard exchange theorem, because we do know that we have at least one spanning set with just exactly n elements. So to see why this extended set would have to be linearly independent, just think about about why that would be. Well, we know that V is not a linear combination of V1 through Vn. Okay, so if we had some expression of zero vector as a linear combination of the n plus 1 elements of this set, then that linear combination couldn't involve V with a non-zero coefficient, because if it did, then it would be rearrangeable to express V as a linear combination of the other elements, V1 through Vn. But V was chosen to not be in the linear span of V1 through Vn. Also, we can't have an expression for 0 as a linear combination of just V1 through Vn with a 0 coefficient for V, because the starting position was that V1 through Vn is a linearly independent set. So basically, this is another kind of generally useful kind of thing to think about and to kind of have in your at your disposal, that if you have a linearly independent set and if it's not a spanning set for the whole space, then by adding something into it that isn't already in its linear span, you always create a bigger linearly independent set. And that's sort of the reason why you can't have if you have a space of dimension n that has some basis with n elements, then every linearly independent set with n elements must be a basis. Okay. Lemma 2 says something very similar, kind of a complementary version of the same statement in a way, not exactly converse, but a kind of an analogous statement about spanning sets. So lemma 2 says that if we're in a vector space with dimension n and we have a spanning set that has exactly n elements, then that spanning set must be a basis of V. And one thing that we can note again as a consequence of the standard exchange lemma is that there can't be a spanning set in the vector space with fewer than n elements, because there is a linearly independent set of n elements, given that n is the dimension of the space, so there's a basis with n elements. That means we can't have a spanning set with fewer than n elements. So if we had if we do have a spanning set with n elements, then in order to be a basis, it must be linearly independent. And here again, okay, we'll say, okay, well, if it wasn't linearly independent, then it would have some element that would be a linear combination of the other elements, and we could throw that out, and it would still live in the linear span of what would remain. So if we had a spanning set with n elements that wasn't a basis, then that would have to be because it wasn't linearly independent. That would mean it would contain some element that's a linear combination of the other elements. Throwing that out would leave us still with a spanning set, but that would be a spanning set with only n minus 1 elements, which is impossible because we know that we have a basis which is linearly independent with n elements. So basically, these two lemmas, lemma 1 and lemma 2, they're kind of quite powerful in practical terms as well as in conceptual terms, because what they mean really is that if you're in a vector space that you know has dimension n, and you have a set of n elements in your hands, you don't have to check both that it's a spanning set and that it's linearly independent in order to confirm that it's a basis. It's enough to check one of those two. If it has the right number of elements to be a basis, and if it's either a spanning set or linearly independent, then it is a basis. Each of those ones follows from the other one. They don't have to be separately checked. And then the third remark, so this relates to something that we said last time, and it's kind of, again, the opposite sort of side of the coin to that. The third lemma says that if L is a linearly independent subset of a vector space V which has dimension n, then L, if it isn't already a basis, can be extended to a basis of V. So last time, the kind of statement that we saw analogous to this was that if we have a spanning set, a finite spanning set in a vector space of dimension n, if it's not linearly independent, then you can basically throw out elements until it is linearly independent and is still a spanning set. So every finite spanning set in a finite dimensional space contains a basis of the space that can be obtained by throwing out elements that are not needed until everything that remains is needed. Opposite situation here, if you have a linearly independent subset that might not be big enough to be a spanning set, then you can extend it to a bigger linearly independent set until you get a linearly independent spanning set, which is a basis. So if L is a linearly independent subset, then L can be extended to a basis of V. And to see that, if L is not already a basis of V, then there's some element of V that's not a linear combination of the elements of L. Add that into L to make a bigger set. That's still linearly independent. Okay. If the set that you now have still isn't a basis, if it still doesn't span the whole space, then there's some element of the space that isn't in the span of your set. Add that in, and you have a set that's still linearly independent and now is nearer to being a spanning set. And you can just keep adding in elements until you've reached something that is the span, that does span the entire space. So this one is quite useful in lots of arguments where you have some kind of partial basis that's built up from some objects of interest, and you want to extend it to a full basis. So for example, what it means is, or an example of what it means is, if we just go back to that example about the skew symmetric matrices, you know, there's a set of 3 matrices that form a basis for this particular subspace of M3R. If you want to build that up to a basis of all of M3R, which has dimension 9, then you can do so by adding 6 more matrices into the set of 3 that you already have. And then you'd have a basis for the full set of 3 by 3 matrices that would consist, first of all, of a basis for the skew symmetrics, and then 6 more elements that would bring you up to the whole space. So sometimes it can be of interest to have a basis in mind which contains within it a basis for some particular subspace that you're interested in. Okay, so that's just a few consequences of the developments of the concepts, I guess, of basis and dimension. And the last thing that I just want to mention really today and in chapter 2 is that once we have a basis in mind, then really in some very precise sense, all vector spaces of dimension n kind of look the same. And to see what that means, I guess the key point here is, you know, if you have a basis for a vector space of dimension n, so that means that you have some. So the vector space might be anything, like it might be a set of matrices, it might be a space of matrices, it might be a space of functions, it might be a space of polynomials, or it might be a space of column vectors of a particular, with a particular number of entries. So there are many different contexts in which a vector space of dimension n over a field of scalars could arise. So what we're saying is, if you have any vector space of dimension n over any field f, then it has a basis, which is a subset of the space with the property that every element of the space has a unique expression as a linear combination of these basis elements. Okay. So if we have any element V of this space, then there's a unique expression for V as a linear combination of the elements of the basis B. So, and the coefficients in that expression are A1 up to AN. The reason why we know that this expression is unique is that if there was a different expression for V as a linear combination of the elements V1 to Vn with different coefficients, C1, C2 up to Cn, then if the coefficients are different in the two cases, then by subtracting one of these expressions from the other one, we would get that 0 is equal to some linear combination of the V's where the coefficients are not all 0, and that would contradict the assertion that B is actually a linearly independent set. So essentially what this is saying is, once we have a basis in mind, then associated to every element of the vector space V, we have a list of coefficients which describe that element as a linear combination of the basis elements. So this element V basically corresponds exactly to the list A1 down to AN. So we could write a kind of correspondence like this. V corresponds to A1 down to AN, or if you want to write the A1 down to AN in a column vector instead of in a sort of list like that, you could write it like that. Okay, so once we have the basis V in mind, then every vector corresponds to a different set of coordinates with respect to this basis. And I suppose one thing that I should mention, which is kind of often not really mentioned explicitly, but is certainly part of the picture, is that in order for this to make sense, the basis is kind of considered to be ordered. Like it's not really just the set V1 to Vn. V1 is recognized as the first basis element, V2 as the second, and so on. So that when we see a list of coordinates like this for some element, we know that A1 corresponds to V1 and A2 to V2 and so on. So the basis is kind of really an ordered set where it has a first element, a second element, a third element, and so on. So we can refer to A1 to AN as the coordinates of V with respect to this basis. And with this association, we can consider V to be represented by the column vector whose entries are A1 through AN. Sorry, that's a bit illegible. I'll just tidy it up a bit. So we're saying that the vector V basically corresponds to that column vector. Okay, so Fn, this F with a capital, with a superscript of n, is notation for the space of all column vectors of length n with n entries, whose entries are in the field F, so Rn or Qn or whatever. So really what we're saying that for any vector space of dimension n, so it might be a space of polynomials or matrices or skew symmetric matrices or whatever it is, once you have a basis in mind for it, then every element of the space, no matter how abstract they are or how they're defined, can be associated with just a column vector with n entries. So we have this correspondence between any vector space of dimension n and this vector space consisting of columns with n entries. And indeed, we have multiple correspondences of that nature, because for any given basis, we get a different correspondence. Okay, so this association of each element to its coordinates with respect to some basis gives us a bijective correspondence between our vector space V, whatever it is, and the more concrete thing, the vector space of all columns with n entries over F, which if you like, of course, you can think of as the space of all n by 1 matrices over F. So it means we can identify these two vector spaces as being really the same thing. And that if we want to know all about vector spaces of dimension n, then in some sense, we really only need to understand the space of all column vectors of length n over our field F. Okay, but of course, the situation is kind of slightly complicated by the fact that, in fact, we have multiple correspondences relating to different choices of basis, and how to kind of manage different choices of basis is one of the things that we'll be talking about in chapter 3 of our lecture notes. So that's it for now. That's also it for chapter 2. We'll pick up again next week with some talk about how to manage more than one basis at a time. Thank you, everyone. Good luck.